A block of root 3 kilogram is attached to a string whose other end is attached to the wall, and force F is applied so that the string makes an angle of 30 degree with the wall. Tension T is given. Okay, so we have the wall, the string, block whose mass is root 3 kilogram. Force F is applied. M3G represents the mass of the string. If we assume it to be massless, which is not directly given the question here. Well, if you assume this to be massless, then this force becomes eliminated. So now what we'll do is we'll have to understand, we'll have to derive the value of tension. So first thing that we should, the moment you hear about tension, the first point that should come into your mind is that tension always acts away from the point of contact. It always acts away from the point of contact. So if we have the point of contact, let's say, the point of contact is point of contact between the block and the string. Okay, point of contact between the block and the string. And when you have the point of contact as the point of contact between block and the string, then it is this point, right? Because this is where the block is attached. So this is the region where the block is attached to the string. Now at this point, what I'll do is I'll apply this principle. Tension acts away from the point of contact. So this is the point of contact. Tension will act away from it. This is the point of contact, and therefore let me use okay, give me a second. So I can say that tension acts away from the point of contact like this. Okay, so what does this represent? This represents the tension in the string, which is T. Now this tension is acting 30 degree with respect to this wall. Okay, now if I draw another parallel line here by alternate interior angles, I can say that this 30 degree is equal to 30 degree here, and if you consider this as vertical here, now I can say that tension T is acting at an angle 30 degree with respect to the vertical, which means that the tension T has to be now resolved. So let us spend some time in detail, or some time to understand the concept of resolution in detail. So how do we do that? We choose the force here. What is the source that we are interested in here? The force that we are interested here is the tension. So maybe I can mark tension like this here. So say this is the okay. So this is the tension which is acting away from the point of contact. This is the point of contact. This is the point of contact, and here the tension is acting like this. Tension acting away from the point of contact. Now I can mark tension here one more time. So tension is acting away from the point of contact. Now when the tension is acting away from the point of contact, we can resolve this tension into two forces. One which is parallel, let's say one which is like this. Okay, maybe I'll use a different color here. One which goes like this, right? And the other which goes like this. So you may be asking now how to select this outward or inward. See, the logic here is very simple. This force, when resolved into two components, the components will show the similar characteristics of this force, which means, is this force going outwards or inwards? If you consider this as a reference axis, this force is going outwards, which means the two of the components will also go outwards. Or in a much critical, maybe I can just use one more arrow to show you that. So say this is the main force, right, which we are trying to resolve. If the arrow is pointing outwards, then arrow of both the components will also act outwards. So what would be the case if the force was coming the other way around, that is inwards? Then these two arrows will be acting inwards. Okay, maybe we will discuss about that when a specific question comes up. Next step is to draw the triangle and find out sin theta and cos theta. So this is the main triangle here, right? Okay, now you might be wondering, if the vector was here, how did it came up here? It's very simple. See, this vector, by laws of vector, we know that these vectors can be changing their position, and yet what happens? The it makes no difference to their properties. So I can take this vector, I can keep it here, I can keep it here, I can keep it here, I can keep it anywhere on the board, and the vector's or property doesn't change, which means I can keep this vector and I can keep it over here. Okay. Now instead of this complete diagram, I have taken only the triangle here, and this is the triangle, and the hypotenuse of the triangle represents the what? Represents the tension T, and this is the vertical component, we'll write as Ty, this horizontal component which we'll write as Tx. Now if we complete the triangle, then we can write down the sine and cos in the respective triangle here. So what is sine 30 here? Sine 30 will be opposite by hypotenuse. Opposite is Tx. So Tx by hypotenuse is Tx. So what is Tx? Tx is equal to T sine 30. Now if this is 30 degree, what is cos 30? Cos 30 will be adjacent by hypotenuse. What is adjacent? Adjacent is Ty. What is hypotenuse? Hypotenuse is T. Therefore cos 30 is Ty by T, and therefore what is Ty is equal to T cos 30. Okay, so I hope these two concepts are clear. If these resolution concept is clear, I think now we can do this question in a much faster way. So now I think the resolution can be done like this. What is this? This represents Ty. What is this element? This represents Tx. And what did we derive Ty as? Ty was derived at T cos 30. And what is Tx is equal to? Tx is equal to T sine 30, right? Coming to the free body diagram of the string. Now what I'm going to do is I'm going to take one small element of string here. And if I consider the various forces acting on this small element of string, I know that the primary force acting on it is √3 kilogram. Therefore it has √3 kilogram mentioned here, right? The second force is the horizontal force F, which is acting like this, F. And this tension which otherwise was acting like this, I have replaced this tension with two different horizontal and vertical components as T sine theta and T cos theta, which means I can essentially let the tension T be there. Okay. Now let us see, since this body is in equilibrium, I can say that sigma Fx is equal to 0 and sigma Fy is equal to 0 as well. Now what is sigma Fx equal to 0 implies? It implies that all the forces acting in the horizontal direction in the left should be equal to all the forces acting in the right horizontal direction, which is sigma F right. Let us see which of the forces acting in the left direction. It is T sine theta. So I can write here this as T sine theta is equal to F, which is acting in the right direction, which is F, right? Now what is sigma Y is equal to imply? Sigma Y is equal to 0 implies all the forces acting in the up direction should be equal to all the forces acting in the down direction. Which are the forces acting in the up direction? The only force acting in the up direction is T cos theta. So I can write it over here that T cos theta is equal to, what is the force acting downward? It is √3 kilogram. So I can write here it's actually weight of √3 kilogram. So that should be √3 into 10, right? And now what is T into cos theta? What is theta here? Theta is cos 30. What is cos 30? Cos 30 is √3 by 2. So this is T into √3 by 2 is equal to √3 into 10. √3 by √3 is 1. So what we are left is T is equal to 2 into 10, which is 20 newtons. Okay, I made it a bit lengthy because I wanted you to be very clear with the concept of resolution of force, because much often what I say is students get confused with the horizontal and the vertical. Now what I wanted to do is I wanted to do the same question not with respect to the vertical. I want you to resolve this force tension with respect to the horizontal and then check if we are getting the same answer. All right. So yes, so that's it with this question. Let's move on to the next one.